I wanted to share my journey of learning about multitasking, parallelism, and concurrency with you guys. That's why I'm starting this series. And today we'll take a look at how multitasking evolved through time. Initially, there was no concept of threads, and processes used to compete for time on the CPU. And there was this concept of cooperative multitasking that was widely used back then. So in cooperative multitasking, each process divided its execution into atomic operations. So the responsibility for dividing its execution into atomic operation was with the process, and atomic operations had to be in such a way that they couldn't be divided further into smaller operations. The processes were responsible for giving back control to the other processes. So the execution would look something like this. If there were like three processes, one of the process would run its atomic operation, give back control to the other process, and this thing continued. For this to be fair, you had to trust other programmers to write good code and not end up blocking the CPU for a long period of time. So if you had a process whose atomic operation would take a bunch of CPU cycles and block other processes from running, then that would be a big issue, right? So that was one of the big pain points of cooperative multitasking, where one process would take up a lot of time on the CPU and starve the other process of CPU time. And to decide on these atomic operations was really difficult. And there was no standard way of deciding these atomic operations as well. So these were the two pain points of cooperative multitasking. Trusting other folks to do their job in the right way seems a little bit risky. So that's where preemptive multitasking kicks in. Earlier, we had to depend on others to implement their atomic operations in the right way and not end up blocking the CPU. But trusting others is really risky. So, in preemptive multitasking, what happened was the logic for preemption or yielding back control to other processes was moved out from the process to the operating system. Now we had the scheduler service sitting at the operating system that would handle the yielding back control part or preemption part, and that decided on how the scheduling strategy was. And mostly all these operating systems, the scheduler in the operating systems, uh, try to fairly give out time to each process on the CPU. And earlier atomic operations were not like standardized, so each process decided on its own atomic operation. So uh, now what happened was the atomic operations were dependent on the CPU architecture and the instruction set of the CPU. The instruction set of the CPU decided on what the atomic operations were. These are normally arithmetic and logic operations, and there are a few other set of operations as well. So now we had fair scheduling, and we had standardized atomic operations. But the main issue here was that now we had the scheduler which took time on CPU. So what happens is, now let's take an execution for example. So we have like three processes here. Process 3 would run for some time, and scheduler decides it's the right time to evict process 3 and give time to process 2 maybe. So the scheduler code had to run in between. The scheduler code had to run in between and then preempt the process. The same thing had to be done for the other process as well now. So to give control to P1 now, again scheduler code had to kick in and process 1 would get time on the CPU. Now all these runs were happening in the kernel space, and these were happening in the user space. So when switching between processes, the context switch was really expensive because you had to take out page tables and pages out of the memory and get in page tables for the process that was being given time on the CPU. You had to flush the transition look aside buffer because these processes didn't share the heap space, so they had their own heap space, and they had their own memory address space as well. So there was a lot of overhead in switching between processes, and a lot of time was wasted on switching between these processes as well. So there was a lot of time occupied by the operating system, and that was like one of the major pain points here. So the context switch was expensive, and operating system took out most of the execution time here. Pain point in the previous approach was that the context switch incurred a lot of time. And this was because the heap space was not being shared and the memory address space was not being shared. The operating system code had to kick in, and there was a context switch from the user space to the kernel space. Then the operating system had to make a lot of syscalls to get the pages out of the memory and the fresh pages into the memory. We had to flush the translation look-aside buffer and a lot more things to switch between processes. So the operating system ended up taking more time on the CPU than the actual execution itself. So that was one of the pain points there. So multi-threading, in case of multi-threading, the threads were confined to the process. So all these threads shared the same heap and the same memory address space. So the context switch was comparatively faster than context switching between processes, and it had less overhead as well. So if we have like two threads, the context switch would really take less time because we just had to switch out the stack, the registers on the CPU, and the instruction pointer. Instruction pointer would point to the current executing instruction. So the amount of time taken by OS for the context switch was drastically reduced. But still, there was some time occupied by the operating system to do the context switch. That was like one of the overheads again. The context switch was still there. Uh, if we had like a lot of threads running, the operating system would end up taking more time on the CPU than the execution itself again. Finally, we have reached the concept of virtual threads. Before moving further, we'll recap on what our goals were. The main goal was to ensure that the scheduling of all these processes on the CPU was fair and each process got fair amount of time on the CPU, and to ensure that no process blocks the CPU for a long enough time and starve other processes, and to ensure that atomic operations were like standard, not just other people to define good atomic operations, and to reduce the time occupied on the CPU by the operating system for context switching. We want actual work to be done. We want the CPU to be utilized for actual execution time rather than utilizing the CPU for scheduling. So we wanted to minimize the time operating system took on the CPU to do the scheduling, do the context switch. So let's see how virtual threads achieve this. Let's say we want to schedule like 1,000 concurrent tasks onto the CPU. In case of virtual thread, what we do is we'll have like a bunch of threads in a thread pool. Let's say we have like 5 operating system level threads, and we'll have like a scheduler at the user level in the application itself, which would do the scheduling of all these concurrent tasks that need to be run concurrently on the operating system threads. So let's compare how the normal threads would stand against the virtual threads. Let's take 3 threads for this example. So we'll have 3 virtual threads and 3 normal threads. So in case of normal threads, the operating system would take some time to switch between these threads, right? So our goal is to minimize this time taken by the operating system to do this context switch. So in case of virtual threads, what happens is there's a scheduler at the user level that schedules all these tasks. Let's assume that we have like 2 threads in the thread pool. Let's say these 2 tasks share the thread. What happens in this case is T2 executes, and when T1 gets its time, there's no need of switching to the operating system. There's no need of switching to the kernel space, do some syscalls, and back to the user space. The program, the application itself schedules the other thread, the other virtual thread, onto the operating system thread, the same operating system thread, and these tasks work concurrently. And there's like a context switch when the third thread gets scheduled on the other OS thread probably. So that context switch would be there. And what happens is if you have like 1,000 or 2,000 concurrent tasks that need to be performed concurrently, this would end up saving a lot of time because there's less switching between the kernel and user space. So that's how virtual threads achieve the performance gains when compared to the normal threads. That's it for this video. I hope you got to learn something new from this video. Please do consider subscribing to my channel, and probably tune in for the next video to learn more with me about multitasking, concurrency, and parallelism. Thank you again.